All right, silly people, here's the situation. We're going to be computationally calculating a value of the Stefan-Boltzmann constant using the methods that we have figured out so far. So the idea is first of all, you need to have this equation for the intensity of a thermal radiation dependent on a frequency. Um, and that's also an intensity per unit area, right? Uh, and to do the calculation of Stefan's Boltzmann constant, you have to integrate this with respect to omega, um, and then end up with this form here, which is representing the energy per unit area, overall frequencies, right? So to get to this form, you take your intensity equation, and again, uh, you integrate it from 0 to infinity over omega. So you get sort of this thing here. Um, and then what you do is you take a transformation of variables, you sub in x for h bar omega over kbt, um, and then calculate what the Jacobian is based on that. Plug that into the integral, and now you have the integral of the same form as you have up here, but then you just need to work out your constants, and yeah, if you work out your constants, you get the same thing as what is in the proof, so that's cool. But to do this computationally, turns out computers don't much like whenever you set the upper bound of your integral to infinity. Instead, what you want to do is you want to sub x for z over 1 minus z. If you do that, then the integral is a lot more easy to calculate. There's me just plugging in that sort of thing into the integral, and then with the proper 1 over 1 minus z squared for the Jacobian, um, plugging that in, you get the final form, which is 1 over 1 minus z to the fifth times z cubed divided by e to the z divided by 1 minus z minus 1. So that's the integral that we're going to calculate and compare it to sigma, which is the Stefan-Boltzmann constant. No plotting in this one. We're just going to get a numerical result, so that's nice. But I am going to go ahead and import numpy as np so I can get that lovely exponent function. So first of all, just going to write the integrand as a function of z, which is going to be z to the third, so return z to the third divided by, you need an exponent, exp of z divided by 1 minus z, and then you subtract 1, but then you also divide that by 1 minus z to the fifth. So let me put that in another set of parentheses for readability. Yeah. Okay. We're going to define some physical constants. So that's going to be kb, the Boltzmann constant. That's 1.381 e to the minus 23. We aren't going to be including t because we're going to be comparing it against sigma times t to the fourth. So we really just need sigma. So basically, we're going to be calculating this equation without the t to the fourth. So that's cool. Then we are going to need c, which is speed of light, 3e8 or thereabouts. And then what was the next one? H bar. So that was, I think, 1.054 e to the minus 34. I don't know, let me check Wikipedia. Yeah, that's about it. And this is all in units of like SI units, so meters, seconds, joules, all that jazz. Then to do the integral, I think the best way to do it is actually via Gaussian quadrature. I know it's very black box compared to like Romberg or Simpson's rule or trapezoidal rule, but the thing about Gaussian quadrature is that it handles singularity really well. And what I mean by that is that we have an integral that is going to be from 0 to 1. This little z over 1 minus z sort of thing here, when z is equal to 1, that means that that denominator is 0, which means you're going to have a really high exponent pretty much, which means it's a really high denominator for the return function. So Gaussian quadrature can kind of handle that already. It's kind of built into the thing to handle that singularity. So that's what we're going to use, and I'm going to use n equals 64 slices of Gaussian quadrature, and then I'm just going to grab the code slice that we used for that in the past, which is just this guy here, the very standard Gaussian quadrature sort of thing that is used in the book. So I'm just going to put that here, and then backspace it a level so it's not, because it's not in a function or anything in this. There we go. Yeah, that should be fine. And then at the end, we can print out the value of the integral s times all the constants that we did. So kb to the 4th. Put that in parentheses, and then divided by 4 times pi squared, and then put that in parentheses as well. I think I have too many parentheses now. No, I'm good. Times, what was it, c squared, and then times h bar to the 3rd. Yeah. Let's see what that prints out. First of all, amp is not defined. I put an extra argument in there. We don't need that anymore. And it print out 5.67 times 10 to the minus 8. I'm just going to ignore the overflow and the exponent line that it just said there because, yeah, of course there is. And it's kind of hard to get around that. But I'm just going to take that result as it is. I will say that the more accepted value of the Stefan-Boltzmann constant is 5.6703 times 10 to the 8th. So, I mean, we got a pretty close answer considering how small the number is. So I'm not too worried that we got 0.677 instead of 0.670. I think it's pretty good.